Welcome to Air Academy Associates series on using SPC Excel. The video clip I'm going to show today addresses a graphical tool called a scatter plot. Sometimes it's also called a scatter chart. But the scatter plot is very useful for determining relationships between two variables. We measure it on a continuous or numeric scale, and I'm just showing you three examples of relationships. If our scatter comes out in one big glob like this, that tells us there's really no relationship between x and y. There's zero correlation. If the scatter comes out like something like this, there's a positive relationship here, because as x gets bigger, so does y. That's called a direct or a positive correlation. There's also a negative relationship, like the third example at the bottom here, whereas x gets bigger, y gets smaller. That is a negative correlation and indicates an inverse or a negative relationship. For example, you might see something like this when you look at x being shoe size and y being the height of an individual. Clearly, as the shoe size gets bigger, as x gets bigger, the height of the individual gets bigger. That's not necessarily a causal relationship, but it is a positive relationship. That is, if you know one, you can predict the other one, but not necessarily a causal relationship. There's things called genetics that influence both the foot size as well as the height of an individual. A negative relationship, like the one shown down here, could be something like x's age. As age gets bigger, y, maybe bone density, gets less. So that is a negative relationship. Now, there are diagnostics we use to quantify these relationships, and we're going to show you that as well. So let's take an example here and talk about it before we get to the software. Suppose we have 22 patients, and we've looked at two variables associated with each patient, namely how much contact time they had with the physician and their resulting satisfaction rating that they gave for that session. So, I want you to know that when we talk about a relationship between two variables, there are two measurements being taken on the same entity in the sample. The sample is 22 patients, and we're measuring two things on each patient: the contact time and the customer satisfaction, or the satisfaction of the patient. And so, this 10 right here goes with the 25. You cannot randomly reproduce this column of data. The 10 and the 25 go together. The 8 and the 20 go together. So when you see the scatter plot coming up, you're going to see 22 data points. This is going to be the x value. This will be the y value. The leftmost column is going to be shown on your horizontal axis, and the rightmost column data will be shown on your vertical axis. We would like to check if there's a relationship here. And if so, how strong is it? Well, this is easy. To get a scatter plot in SPC Excel, all you have to do is highlight your data, which we typically do first. Then we go to Analysis Diagrams, which is a main menu item from the Sigma Zone ribbon on SPC Excel. And we go down and we highlight Scatter Plot. Once we click on Scatter Plot, you will be asked to show where the data is stored. Well, we've already highlighted the data, so we can just click through Next on that. Just come down here to Next and click on that. And up will come a Trendline Options User Interface menu. We're going to talk about that, but when you close out on that, after you've selected some options, you will get the scatter plot as shown here. You will also get a line through the data, which is called a regression line, the equation of which is shown right here. The R-squared is a nice diagnostic of the regression analysis that tells us how strong the relationship is. This R-squared will be a number between 0 and 1, and the closer to 1 it is, the stronger the relationship. The closer to 0 it is, the lesser the strength of the relationship. So this is the scatter plot. There is this R-squared. I'd like to say a couple of things about it before we go to the software, and that is R-squared is a measure of the strength of the relationship between the variables. Let me give you three examples of R-squared, which must be Any r squared is going to be between 0 and 1 inclusively. R squared of 1 means we've got a perfect fit. The line or the curve goes through all of the data points. In other words, all of the data points lie exactly on the line or curve. And r squared of 0.7, the points are not on the line or the curve, but they're close. The scatter is pretty tightly clustered around the curve or the line. When you have an r squared of 0, that's basically a glob of data. It doesn't matter what kind of line you put through there. None of it is going to be a good fit. A little rule of thumb on the values of r squared, if it gets to be up there around 0.5, we say that's a moderate relationship. If r squared gets to be 0.7 or more, that's a strong relationship. And if r squared gets to be about 0.9 or more, then there's a very strong relationship. So just to give you kind of a feel graphically and with some words here to give you an idea what you're looking at, and when this diagnostic r squared pops up, what it really means. So let's go to the software now and take a look at. Here we are looking at 3 different data sets, which we will get scatter plots for in a second. The first data set, contact time versus patient satisfaction, is the leftmost. We'll reproduce the scatter plot using the software here, just like we mentioned in the PowerPoint slides. I just want to mention that you have labels here. It would be a good idea to include the labels on the column headers because contact time will be printed out on your horizontal axis and patient satisfaction will be printed out on the vertical axis. So if you do not highlight the labels, you will get factor 1 and factor 2. That's what the software will call your first column, factor 1, and it will call the second column factor 2. But we have more specificity here. That is, factor 1 is really contact time and factor 2 is patient satisfaction. We highlight that, go to Sigma Zone, go to Analysis Diagrams, and click on Scatter Plot. We have already highlighted the data, so I'm going to click through this to the next chart, which is the scatter plot itself. We also have some trend line options that crop up over here. Let me talk about that. But here's your r squared as shown in the PowerPoint, about 0.67. That's a fairly strong relationship. We also have y equals 0.2588x plus 3.5818, which is the equation of the regression line. That is the best line that goes through the data. Regression analysis is also sometimes called curve fitting, because it will put the best line, in this case we ask for a line, and that's the default setting. When you first click on scatter plot, this is what you're going to see. Okay, but you can change this. Looking at r squared of 0.67, let's say we put a second degree polynomial through that. I had just clicked on polynomial. You can change that to a third order or even a fourth order, which doesn't really make much sense. The r squared goes up a little bit to 0.71, but the point is that would a fourth order polynomial with an x to the fourth, x to the third, would that really describe the relationship? I don't think so. You want a simple relationship such as the linear relationship. The r squared is almost 0.7 here, and it's a very simple way to quantify your relationship. So you have that. If you don't like the r squared printed out, you can remove that by unchecking down here. You can even remove the equation, okay, if you care to, or you can put them back in if you care to. You can even remove the line itself. I guess if you don't display the line itself, you wouldn't want the equation. So let's say we take everything off except for the points themselves. So I'm going to right click on that line and it says format the trend line. Click on that. And now, sorry about that. Oh, I don't even have to go to format trend line. I can just delete right here. I don't have to format the trend line. I can just delete the line directly right there. Now, if you want to bring it back, just come back up and undo what you've just done. But again, right clicking and just deleting deletes the line, and so you just have the scatter. Maybe that's all you want to show, but typically it's a good idea to put the line through there simply because it's a nice little tool that we can use for predictability and getting the equation back on the chart sometimes the equation and the R squared get in the way of the scatter, so just highlight those guys if you need to and drag them over somewhere on the chart that does not interfere with the graph. In this case, it didn't at its default setting, but sometimes it does depending on where your scatter plot is going and the line as well. So this is your scatter plot, and it's a great little tool for analyzing and quantifying the relationship between two variables. Let's take another data set. This is a very famous data set, actually. This concerns the shuttle, space shuttle, the first 24 launches of the space shuttle, where the temperature at launch was provided, as well as the number of O-ring failures during those launches. So, is there a relationship between temperature and the number of O-ring failures on the first 24 launches of the space shuttle? That's what we'd like to investigate. Obviously, the 25th launch of the space shuttle was Challenger, and we had an accident, a disaster. So let's take a look at this temperature versus O-ring relationship. So let's go to analysis diagrams, bring the scatter plot up, click through, we've highlighted the data, and the graph starts on the horizontal axis at 0 degrees when the lowest temperature we'd ever launched a shuttle at was 53 degrees. If I put my cursor on there, I can see, if I get it on the point there, it'll show ultimately 53, and it doesn't look like a good fit. The R squared is pretty low, 0.321, and this is way too much wasted space. So I'm going to cut back to 30 degrees, and the way we can do that is we can change the scale on the horizontal axis. So if I click on the scale and then right click, you will see format the axis. If you click on format the axis, you can change your minimum up here from what it was, a 0 to a 30. That will get rid of the left side of this chart and give us more chart for the graph and the scatter points that we want to really look at. You can also change the major unit here from 10 units, say. You want a scaled hash mark on the horizontal axis every 5 units, like every 5 degrees. You can change that. And so we've got a scatter plot right now that looks like this. And the reason I went to 30 is because we're going to extrapolate this curve out to 30, because they were going to launch the Challenger at about freezing and around 30, 33 degrees the next morning, and they were making a decision whether to launch or not. Is there a strong relationship between temperature at launch and the resulting number of O-ring failures? Let's take a look. Now this R squared is not good, so you know what I'm going to do? I'm going to try to put, and I clicked on Format Trend Line, I'm going to put a polynomial of degree 2 through that data. And let's, at the same time, let's extend this graph 23 degrees to the left, say all the way to 30 degrees, because the lowest data point is 53 there. And so I'm going to forecast backwards 23 degrees. Now the graph goes off the chart on the top side, so we're going to have to readjust the vertical axis. So you just click on the vertical axis and then right click and do format axis, and here you get your minimum and maximum again. So the minimum of 0 is okay, but the maximum, let's jump that up to 12. And now you can see the full curve going all the way out to 30 degrees, and this is a scatter plot with the corresponding R squared for the quadratic equation, the R squared being about 0.49. So what that means is temperature explains about 49% of the variation in that data. And if we were to predict out to 30 degrees, we'd be predicting, between 9 and 10 O-ring failures. And that's under the assumption that the relationship between temperature and number of O-ring failures continues to the left here, as it has in the range of the data over which we've collected. So this is a scatter plot for the O-ring failures. Now, let's take one more example, and suppose you have the hypothesis that in knee replacement surgery, there's a relationship between age and the length of stay in the hospital. It's normal to think that maybe the older people who have knee replacement surgery are going to stay longer in the hospital after the surgery. Well, let's check it out. There were 45 patients who were followed after their knee replacement surgery, and the length of stay was recorded along with their age. And we come up here, highlight the data, go to analysis diagrams. This is easy getting scatter plots. Just click on next, and here's our scatter plot. Now the R squared here is quite abysmal. Abysmally bad, that is, 0.0011, and that means there's no relationship whatsoever. Even if you were to put a curve, a polynomial through that, the R squared is still 0.03, and so even if you put an exponential through that or a logarithmic curve through that, none of it is good. So here's an example of a scatter plot that shows no relationship between age and length of stay in the hospital following knee surgery. So here are three examples. The time versus patient satisfaction, fairly strong relationship. Temperature versus O-ring failures, kind of a moderate relationship here, but one that caused great consternation at NASA back in 1986. The age versus LOS, length of stay, no relationship whatsoever. That's the beauty of the scatter plot. The scatter plot, along with a diagnostic called R squared, can be very, very informative in interpreting data that gives us a clue as to the relationship between two variables. Thank you very much. That concludes our presentation on the scatter plot.